All right, so today we're going to go over clouds and pressure. As you can see, there's a couple clouds, different types of clouds right here. So what are clouds? Clouds are tiny droplets of liquid water and or small ice crystals suspended in air. There are three things that you need to have for any cloud to form. First off, there has to be moisture in the air, water vapor. Second off, there has to be presence of condensation nuclei. We'll get to that in a second. And third, you need cooling temperatures. So what is a condensation nuclei? A condensation nuclei is, well, they are aerosols or airborne particles in the atmosphere, which provide surface for water molecules to condense on. What could be a condensation nuclei? Well, first off, you have ash from volcanoes, because when volcanoes explode, they spew out a whole bunch of ash. That is considered an aerosol. Then you've got dust from desert winds, and last but not least, salt crystals from the ocean water waves. Remember, when the waves crash, you've got evaporation going on. What's in the water and ocean? Well, salt's in it. Where does that salt go? That becomes condensation nuclei. And then last but not least, you have chemicals in the air. That could come from like smokestacks. It can come from cars. All of those nasty chemicals that go into the air become um, condensation nuclei. All right, so now we have this thing called adiabatic cooling. So I'm taking it a step further. How do clouds form? Well, as air rises, and remember, air typically has water vapor in it, it's under less pressure. So it's all tightly together when it's down towards the surface. And it's moving a lot of energy. As it goes up, it starts to expand, and it's losing this energy. And that energy is keeping it warm. And as it gets farther and farther apart, it starts to cool. Well, what happens when it cools? It hits its dew point temperature, which we've talked about before. And that dew point temperature means it's going from a vapor to a liquid. And it condenses on the condensation nuclei, which then begins to form those clouds. The whole process is called adiabatic cooling. So when it goes up, it's called cooling. But in the right conditions, it's reversed and it goes down and it's called adiabatic heating. All right, so this is just a picture of some of the clouds that can form. These are common clouds. You've got cumulus, you've got stratus, you've got strato, you've got cirrus, cumulonimbus for those of you who watched Up. I keep forgetting his name. I want to say it's Doug, not Kevin. But he mentions a cumulonimbus cloud. These are really, really kind of dangerous clouds, which we'll go into in a second. And then you've got this stratus, steady precipitation. This is going to come into our lesson a little bit later. So those dangerous clouds that I'm talking about, right? Those are, if the conditions are right, adiabatic cooling and cloud formation produce really, really rapidly. And when that happens, it can form some thunderstorms, or even if they grow in intensity enough, they can form tornadoes. So what happens is you have all this hot air. Remember, the hot air is at the warm air is at the bottom because it's a lot of energy. As it rises up, and it gets cooler and cooler, and you can see it's rising up in this stage where you're getting those big, huge, fluffy clouds. And all this warm air is going up. Well, all of a sudden it starts hitting that dew point. This warm air, some of the warm air is getting the dew point, so it's coming down, and that's where you get that heavy rains. And towards the end, all that hot air has gone up and it's starting to cool down, and then it gets lighter rains. Well, if this happens fast enough, it shoots all the way up, just like you saw on the last page, and it forms like an ample thing. And this is where you have lots of dangerous thunderstorms, possible tornadoes. All right, now we're going to look at some pressure. So air creates pressure, which means it has weight. I know it's kind of weird, right? So the force of gravity causes air to have weight because gravity is pulling down on everything, pulling down on our atmosphere, keeping us all together. If there was no weight to the air, everything would be floating around and like we wouldn't be here. So think of it like being at the bottom of a pool. I'm not sure if you've been at the bottom of a pool, but like the 12-foot pools, as you go down, you can start to feel like all this pressure on you as you get closer to the down 12 foot or even 6 foot. Like the farther down you go, the more pressure you feel on yourself. And as you go up, the less pressure you feel on yourself. That's like air, only you don't swim in it, you breathe it. All right, so looking at this, air pressure acts equally in all directions. Like we have pressure on us right now. You don't feel it, but it's hitting you equally. With any and also within any objects containing air, like buildings and the human body, and empty bottles like this, which is empty. Has the same pressure out here as it does inside the bottle. The actual air pressure at sea level is about 14.7 pounds per square inch. So you have more pressure at sea level than you do probably where you are right now. All right, and now how do we measure this thing? Well, air pressure is dependent on altitude, how high up you are. The higher the altitude you are at, the less atmospheric pressure is around you, the lower the air pressure will be. So you have less atmosphere as you go up, which causes less air pressure on you. Like it doesn't press on you as much. Pardon me, which is why the mountain climbers for Mount Everest, they have to like stop ever so often because they could get altitude sickness because they're not used to having less atmosphere on them, and plus like the oxygen thing. There's not as much oxygen up there as they need to breathe. So these things right here, we saw one way back at the beginning. They are barometers, and they come in hundreds of variations, but of two basic designs. You've got the mercury or HD barometer or an aneroid barometer. So right here, we're looking at an HG barometer. These were the first barometers, and it came with liquid, some type of liquid, either water or mercury, in a glass tube that was inverted into a pan of the same liquid. As air pressures increases, the mercury in the glass tube would move up, and vice versa. As it decreases, it would move down. Okay, because the air pressure is pushing on that liquid, which in turn pushes it up into this scaled tube. At sea level, the height of the mercury is in the inverted tube would be high, which is where they would calibrate it or standardize it. So barometers typically are measured in inches of mercury with 1 atmospheric pressure equaling 29.92 inches. And now you have an aneroid. Well, what's an aneroid? Well, this one has a vacuum barometer. The other one was just liquid sitting there and getting pushed up and down. Now you have a vacuum. It's a little bit more complicated. It consists of an airtight metal box, which with a partial vacuum. So like this would be in a box. And in the box, as a change in air pressure causes the spring right here, the spring to move, which causes the spring force causes this spring to move, which in turn moves this, which moves the chain, which moves the hand. These usually, when measured, has millibars, which is not millimeters of mercury. They're two separate things as units, but also have an equivalency scale in inches of mercury. So, there are two scales. You've got millibars and inches of mercury. And remember, we're looking at this as 1 atmosphere. Everything is related to 1 atmosphere. So how many millibars in 1 atmosphere? 1013.2 millibars. How about inches of mercury? We just saw that, 29.92. And now we're going to do some conversions. We're going to use this right here, page 13 of your reference table, and it does tell you where the 1 atmosphere is. Well, let's look at the millibars. Millibars is on this side, inches of mercury on this side. We're looking at 997. So 996. Each one of these is worth 1. So 97. I'm going to go across, and I'm going to say what, 2944 or 45. I'd be right because there is leeway, plus or minus 1. How about 3015? 3015. Each one of these littles are worth 1. So I'm going to look over here, pop over here, 1021. How about 106? 10656 across, 2971. All right, let's look at this. 29 even is right here. Go across. Looks like 982. How about 1000? I'm going to go across. I'm going to go 2953. 3021. Let's go up here. 3021. Go over here. 21, 2, 3. 1023. And then last but not least, 1019. 1019 right here, across here. 30.9. 0.09. Yes, 0.09. Yep, had my zeros wrong on that. All right, so you're going to do some conversions for homework. Use your page 13. If you have questions, you want me to check it over, hop on Zoom. Remember, you need your reference table every day for this class. And I hope you guys have a great day.